Okay, if we look at the derivative of natural log function, derivative of natural log is pretty straightforward. It's just the derivative of natural log of x is equal to 1 over x. So you take whatever you're taking the natural log of and put in the denominator, provided that x is positive, because the domain of natural log function is all positive values bigger than 0. So if you have, this is a chain rule situation here, if you have a function u in terms of x, the natural derivative of natural log of u would just be whatever your function is, you put that in the denominator, multiply that by the derivative of u in terms of x. So u is assumed to be a function of x. Also, these two statements are the same. The u prime divided by u is the same thing as 1 over u times du dx. So these two statements are the same. And again, we're assuming that our function of u is positive because, again, you can't take the natural log of a negative number. We're going to look at the derivative, how to show the derivative of natural log of x is equal to 1 over x using the definition of derivative. So let's just review the definition of derivative is assuming h goes to 0 of f of x plus h minus f of x all over h. And our function f in this case is ln of x. So I'm just going to plug in here. So we have the limit as h approaches 0. So we get the ln of x plus h minus ln of x over h. And then since this is logarithm and it's a difference, you can write a difference as a quotient. So we still have our limit statement. We have the ln of x plus h all over x all over h. So let's rewrite that. I'm just going to put this 1 over h in front. So I'm going to write this as the limit as h approaches 0 of 1 over h, the ln of x plus h all over x. And I'm just going to break up this fraction up into two different fractions. So I'm going to write x over x and h over x. So I'll show you that now. So I just broke this fraction up here into two different fractions because the common denominator, if you add these two, you'll get this expression here. So it's just going backwards. So now x over x is 1 and h over x is just h over x. So x over x is 1 and then just h over x is h. Excuse me, h over x is just what it is. Whenever you have a coefficient in front of a logarithm, you can write that as an exponent. So I'm going to throw this 1 over h up top here. So now I have this natural log expression here with an exponent and 1 plus h over x. I have to sneeze. Okay, I'm going to do a convenient substitution here. I'm going to let v equal h over x. And if that's the case, as h approaches 0, so as this side approaches 0, that means v also approaches 0. So therefore, v also approaches 0. And it's also true that h is equal to x times v, just by rewriting this, multiplying the x over, just doing a little cross multiplying here. So we have h is equal to v times x. So I'm going to replace h right here with that. And h is equal to x times v, so I'm going to put x times v right here. So you notice wherever there was an h, where's my cursor? Wherever there is an h, I put x times v, where it just came from this, rewriting this here. So therefore the x's cancel here. I'm going to write this as a coefficient. So let me just do that real quick. So I cancel those x's, and since again this is a logarithm, which I forgot the logarithm there, so let me fix that. So I put the natural log back in there. I don't know why that went away. So now I'm going to take this 1 over v, and I actually put it back as an exponent. And this 1 over x, since this limit has to do with h approaching 0, I'm going to move this 1 over x out of the way. So I'm going to put 1 over x up front, the limit as h approaches 0. I'm going to put this 1 over v as an exponent. So the ln of 1 plus v, 1 over v. Now, we don't have h's anymore. We said earlier, as h approaches 0, v approaches 0. So I'm going to replace this limit statement as v approaches 0. So I'm just going to rewrite this just by changing this limit statement to be v approaches 0. So I just changed the h approaches 0 to v approaches 0. And I'm just going to move this ln out of the way and squeeze the limit in between them. So this is 1 over x times the natural log of the limit as v approaches 0 of 1 plus v 1 over v. Now the question is, what is this equal to? So let's use the graphing calculator to help us out with that. Hopefully that's equal to something nice. So let's turn on the graphing calculator. Here's that same thing, 1 plus x raised to the 1 over x. 1 plus v to the 1 over v, same thing, which is written right here. So let's take a look at the graph. The graph isn't that illuminating. So we're looking at as v approaches 0, so we're looking at right around 0. So not too sure what's going on at 0 right there. Unfortunately, if we plug 0 in, we get nothing because you can't have 1 over 0. 1 over 0 in your exponent is bad. So I'm just going to, as opposed to using the table, I'm going to use the vars function in the home screen. So let me just do a little key history for you here. Let me clear that out. I'm going to go to vars, yvars, and a function value. So I'm going to look at y of 0.01. And y of 0.01 is that. Okay, so again, I'm looking at this limit as h approaches 0. Or excuse me, v approaches 0, which in this case is x approaches 0 because our function is in terms of x. So I'm just going to use 0.01. Now I'm going to use a smaller value. So let me just plug that in for you. So I plug 0.01. Now I have another number, which is getting closer to something kind of classic. Well, hopefully you'll see where I'm going with this. Let's try an even smaller value. So now I have 4 zeros and 1. Hopefully that number again is looking more convenient or more recognizable. Let's try another number. Okay, here's another number, and let's try an even smaller number. So here's 10 to the negative 10, so therefore there's 9 zeros. And when we plug that into this function here, which is the same function that we have highlighted right here, we're getting 2.71828 which is conveniently the same as e. Okay, I did that on purpose. I knew that that was going to happen. So the right-hand side, our limit value is equal to, looks like it's getting very close to e. As far as we can see, the calculator numbers are exactly the same. Let's just do this on the left-hand side. I'm just going to put a negative in front of there, so just hang out for a second. And notice when I put in negative 10 to the negative 10th, which is really small, but on the left-hand side, I get the same value as well. So the whole purpose of doing that is that this number here is equal to e. So that limit right there is equal to e. So therefore, we have 1 over x times the natural log of e. Well, the natural log of e is just equal to 1. So this is just 1 over x times 1, which is 1 over x. So we took the definition of derivative using natural log. We took the derivative of natural log using the definition of derivative, and we got 1 over x. The only trick was this piece right here. The best way that we could determine that limit is by using analysis using different values. To find this limit using calculus is outside the purview of this class. That's actually a C topic in BC calculus. So the best way we could do is just plug in values and estimate what that limit is. But conveniently, a natural log of e is equal to 1, so we get 1 over x. So we just proved that the derivative of natural log is equal to 1 over x.